All right, oops, that's algebra 1. Welcome back, everybody. So here's the key for the homework. No. Factoring. They're doing a review of all factoring.
I want to do that.
Factoring easy types, factoring hard types, factoring up, all that, flow chart,
I want to do that.
all that good stuff. Again, pause if you need to, if you're watching along at home. Here's 23, 25, 27, 28, 29. Go ahead and take a look there. Again, I hope you guys see that a lot of these transformations are a lot easier than the types of functions that we've had in the past, because there's really no simplification to do. You know, you really just kind of put the number where it goes, and then that's it. The only difficult piece, I shouldn't say the only difficult piece, one of the difficult pieces about this, though, is that you have to also identify where the asymptote was. But just try to remember that if it's an exponential, the asymptote was the y-axis. So the only time the exponential asymptote is going to move is if you shift up or down. That's the only time. The only time a logarithmic asymptote is going to move is if you shift it left or right, because that was originally the y-axis, x equals 0. Okay? So it's going to shift left or right. So notice here, like number 25, that's a shift of a right 5. And it's a logaritm, so a shifting left or right will actually move.
Please pardon the interruption. At this time, can we have 7th graders, last names A through N, who are getting spring pictures, to please report to the main gym at this time. 7th graders A through N, who are getting their spring pictures taken. Thank you.
So if I shift it left or right, I've literally paused. If you shift it left or right, it's going to move that asymptote right. So here, shifting right 5 moves the asymptote right 5. Make sure if I ask you, I hope this is very clear. If I ask you for an asymptote, I need the equation, right? Don't just say 5. I need x equals 5. Why am I going to be picky about that? Because logarithmic asymptotes are different from exponential asymptotes. Logarithmic asymptotes are x equals. Exponential asymptotes are y equals, because they're horizontal versus vertical lines. Okay. Scrolling down here is 28, 29, all the way through the end. All right, how are we doing this? We do all right? We'll come around with the guided notes for today. You're going to see today, not a lot of homework for tonight, right? 8, 10, 12, 13, 14, 5 problems.
That's scary.
No, it's really not bad. Well, go ahead and get out your graphing calculators.
I think you were on. I literally said.
He's like, why is there food?
All the way to the third question. I can't. Send me pictures. You go to around 3 like, well, I was thinking the right.
I don't know why I was thinking. All right, ladies and gentlemen, let's get started here. So, before I move on, any other questions on the homework that we want to talk through? Anything else? Okay. So what we're going to be doing today is doing those regressions with exponential and logarithmic functions. Okay. This process is going to remain the exact same as it has in the past. We can do logarithmic regressions and exponential regressions just like we have with linear regressions, quadratic regressions, cubic regressions, quartic regressions, all of those. Okay. Now, analyzing data values can identify a pattern or repeated relationships between two quantities, obviously. Take a look at this table for values for the exponential function 2 times 3 to the x. We notice here that it's a pattern. It's not a, if I think back to polynomial functions, and I said, well, the degree depended upon how many sets of differences we could take until it got constant. It's not differences anymore. Okay? It's not differences anymore. It's basically a common ratio. If you can find a common ratio between the y values, you can see that it would be exponential. And that common ratio that you find is actually the base of the exponent. So notice here, you see how this is multiplying by 3 each time? How does that relate to the equation? Well, look at the base of the exponent. It's a 3. What you're continually multiplying by is the base of the exponent. Well, what is that 2 doing? Well, remember that 2 is your starting value. That's your y-intercept, basically. The number sitting out front is your y-intercept, your starting value, and this is what's going to happen. Each successive x term, I'm going to multiply by 3 each time. Okay? It's going to exponentially grow by a factor of 3. Okay? Now, notice that the ratio of each y value in the previous one is constant. Each value is 3 times the one before it. So the ratio of the function's values is constant for equally spaced x values. So what we're going to be doing here is we're going to be creating this function, a times b to the x, right? Remember, a is your initial value, b is your base, and x is your exponent. Yeah, we talked about common differences. Determine whether this is an exponential function. If so, find the constant ratio. So let me ask, is this exponential? Well, I should be able to tell, if this is truly exponential, I should be able to tell what I could continually multiply 2 by to get to 3. And then that same value, 3 by to get to 5, and then 5 by to get to 8, and then 8 by to get to 12. So let's see, what would I multiply 2 by to get to 3? Well, if you're struggling with that, you could create this really simple equation. 2 times what is 3? Right? Okay, so this is going to equal 3 over 2, so 1.5. This is multiplied by 1.5. Is that true for all pieces of data? Let's check it. I would take 3 times 1.5. No, that's not true. If I take 5 divided by 3, actually, this would be multiplying by 1.6 repeating. If I took 8 divided by 5, this would be 1.6 times 1.6, flat 1.6. If I took 12 divided by 8, that would be 1.5. So do I have a constant ratio? No. I know that this is not exponential. I don't know what it is. Exponential. This is not exponential. I don't know what it is, but at least it's not exponential. Okay. Go ahead and do the next one. See if you can figure out whether that is exponential or not. Is it exponential? Let's check. 24 divided by 16, that would have been, a 1.5, look at that. Times 1.5. Okay, 36 over 24. Look at that, 1.5 times a 1.5. Is that true for 36 to 54? 54 divided by 36. Look at that, 1.5. You should check all of them just to be sure. You never know if it's going to vary in the end. 81 divided by 54 is going to get me 1.5. So, is it exponential? Yes. We see that it is exponential. Now, let's try to, I know it says to just write the common ratio, or the constant ratio. Let's write the equation. Why not? Let's try to. Because I should say, it should be of the form f of x is equal to a times b to the x. Well, what's my b value in this case? What's the base of my exponent? Somebody tell me. 1.5. It's the common ratio. So I know that this is going to be, f of x is going to be something times 1.5 to the x. What's my a value then? 24. 24. And that's my answer. And it didn't really ask us for that, but it's something that we could create access for the common ratio. But the common ratio is really just a base of the exponent anyway. 24 times 1.5 to the x. We only know that. We only know that that's truly the equation because we see the common ratio of 1.5 and we're given the coordinate 0, 24. If we weren't given the coordinate 0, 24, we couldn't create the equation. We didn't know where it would start, okay? It's just a special case where we're given the 0. Usually you are given the 0. Now, down on the bottom of your guided notes, it talks about the exponential regression. In chapter 205, we used linear regression, quadratic regressions, exponential, more polynomial regression. But remember that was basically just fitting data to that certain shape, right? If it was cubic, it was quartic, whatever. Say you were running some sort of experiment and the data came out to look something like that. You would say to yourself, oh, that's probably exponential, right? So what we're going to do is run what's called an exponential regression. This is on the top of the back. Find an exponential model for the data. Use the model to predict when the tuition at UT Austin will be $6,000. All right. So here's what we're going to do. Here's my table of values. Okay. Here's my table of values. I'm going to say let x equal. What do we want to do? Let's just let x equal those values. That sound good? Let's let x equal those values, shall we? So let's go into our calculators and let's modify our lists. You go stat, edit, and let's change what's in our lists. I'm going to clear down. Remember, don't delete, hit clear. And in my list, I'm going to write 0, 1, 2, 3, 4. And in list 2, 31, 28, 35, 85, 37, 76, 39, 50, 41, 88. And I'm going to put on my scatter plot now. Now remember, if you need to do this, this is back in the second chapter of the linear regression document. It's probably, I think I probably linked it into the chapter 5 as well. And probably chapter 6 is the same thing. But now I run my scatter plot. You go into y equals, you clear out anything that's there, and you turn on plot 1. They turn on plot 1. And then you go zoom, stat. And there's my scatter plot. No, I haven't run my regression yet. I haven't run my regression yet. I'm going to bring over this screen. Let's run our regression. I'm going to go back up to my home screen. And then the process remains the exact same. You go stat, calc, and then you keep scrolling. There's our good friends, linear, quadratic, cubic, quartic. And then if you keep going, this is linear regression, just another form of linear. And then you scroll down one more. That's LN reg. What do you think that is? Natural log regression. And then there's exponential regression, and that's the one that we want. If I kept scrolling, I would see power regression and logistic regression, and then sine regression. Yeah, there actually is like sine, cosine, tangent regression. Manual fit, let's not even worry about that. Let's go back up to exponential regression. Exponential regression. That's the one that we want for our purposes here. And there we have it. Okay. How did we know?
Pardon this interruption. At this time, can we have the remaining 7th graders who are taking their spring pictures to report to the main gym? All remaining 7th graders who are taking spring pictures. Thank you.
How did we know that it was going to be an exponential regression? How did we know to use an exponential regression? The wording of the problem. Quite simply, the wording of the problem. So here's my equation. Y is equal to, or f of x is equal to 3235.64 times 1.07 to the x. Now, it gives me both the r squared and the r value. Basically, those are just telling us how strong our correlation is. What would we say? Pretty strong? I'd say. Yeah. So yeah, this is a pretty strong correlation. So let's go ahead and graph it because I want to know what the tuition would be or how long it would take the tuition to get up to $6,000. So I need to graph this. Let's go back into our y equals, and I'm going to put my equation in y1. And remember, to do that, you go vars, statistics, which is choice 5, and then scroll right twice to EQ. So there's my regression equation, and I graph. Here it comes in. Now, at this point, I want to figure out how long it's going to take for the tuition to get up to $6,000. Now, is 6,000 an x value or a y value? It's a y value. So I'm going to go into my y equals and plug in $6,000. 600, here's 6,000. Now, I don't know if I'm going to see it on my screen, so I'm going to zoom fit. I'm going to zoom fit. Usually that works, so let's test it out. Let's zoom fit. There's my exponential coming up. Let's see. Come on, come on, come on, come on, come on, come on. Oh, I guess I'm going to have to zoom out. Let's zoom out. Zoom, 3, enter. Here's my exponential. Come on. Keep coming. Keep coming. There it is. There's my intersection point. Second, calculate, intersect, choice 5. Enter, enter, enter. There it is, 9.07. Let me bring this over here. 9.07. It says it will reach $6,000 in 9.07. Now let's analyze it. Let's figure out what that means in our context. So this is like the year 2000, the year ending 9.07. So this is like 2009.07, right? So if we actually took that 9.07, so we would say really it's in the 2009-2010 year, right? If we really, because it's just a little bit above. But honestly, this number is fine. This number is fine. I would accept any of those. But basically, interpret your answer based on what you see. Question? Yes, sir.
When did 2008 to 2009?
9 point. Let's think about that. 0.07. That would probably still be within like January, February. So I'm guessing if it truly happened in January of 2009, that would be within the 2000. Yeah, you'd be right. 2008, 2009 school year. Yeah. Yeah, you got to think about it in terms of a school year. That's why I'm okay with 2009.07. Okay, yeah, sure. Okay, now, the next thing that we're going to talk about is logarithmic regression. Okay, logarithmic regression. Again, I don't even have the notes up on my screen because it's pretty simple. Many natural phenomena could be modeled by the natural log functions. Notice that my calculator, when I went through and I looked at the regressions that I had in my calculator, when I was trying to find exponential, did I have a common log regression? No, it's a natural log regression. Why? Because most things that happen in the natural world are natural log, not common log. It doesn't make sense to do a common log. It's more often than going to be a natural log. Okay? So how do I know when to use a logarithmic regression rather than an exponential regression? Well, it tells you within the context of the problem. Okay? That's how you know. It says use a logarithmic regression. And when I say use a logarithmic regression, I'm implying that I want you to use a natural logarithmic regression, natural log. All right, so let's go ahead and put in our data. Stat, edit, clear out our lists. Plug in. We got, what do we have here? This is a, define if, when will the speed, so this is just a speed versus time table. So time 1 minute, 2 minute, 3 minute, 4, 5, 6, and 7. And then 0.5, values there. So let's make our scatter plot again. I'm going to go into my y equals, and then I'm going to clear my exponential regression that I just ran, and zoom stat this. Doesn't this look logarithmic? This looks logarithmic. It's got that logarithmic shape to it. Let's actually see what our equation is. Let's quit out back to my home screen and run the natural log regression. I think it's choice 8, 9, something like that. Come on, keep going. There it is. ln reg. Now look at how it's giving it to you. It is a plus b ln of x. Look at that. That's a plus b ln of x. That's telling you how it's giving you the equation. It's not a times b ln of x, it's a plus b ln of x. So f of x equals, or y equals, a 0.587 plus b 2.638 natural log of x. That's our natural log regression. How strong is that correlation? Very strong. Very, very strong. Okay, well now let's plug that into our y equals. Again, you go y equals vars statistics EQ, and we'll graph it. I haven't even looked at what we need to do with this yet. I know I'll probably need to graph it. So. All right. Now, let's see what the question is asking. It's saying, when will the speed reach 8 meters per second? When will the speed reach 8 meters per second? Is 8 meters per second, is that an x value or y value? That's y value. So I go into my y equals, and I say y equals 8. I want to know when the speed is 8. I'm going to zoom fit this. Probably not going to see it on my screen. There's 8 coming across, so I'll probably have to zoom out. Zoom 3, enter. You know, remember, I could have manipulated my window if I really wanted to without using the zooms. I could have just manually gone into my window and just brought it above 8, and I'm sure I would have seen it. So I second calculate the the intersection point. Enter, enter, enter. 16.61. 16.61 minutes. That's how long it would take for the speed to reach 8 meters per second. 16.61 minutes. It asks me another question, though. It says, what will the speed be in 15 minutes if it doesn't reach 8 meters per second within 16.6 minutes, or takes that long to get up to 8 meters per second? Okay, well, what's it going to be at 15 minutes then? Well, the nice thing here is that that's an x value. I say if x is 15, what's y? So I don't need to go back and regraph. I could just second calculate the value of 15. 7.73. 7.73. So that means in 15 minutes, 7.73 meters per second. In 15 minutes, would be 7.73 meters per second. Okay. So, is this anything different than what we had done before? Not really. You know, the process remains the same. I give you your table of values. You figure out the equation. You plug it in your calculator. Find the scatter plot, and then answer the questions based on the graph. Okay. Interpret your results. Any questions? Cool. All right, well then I'll let you guys get working on your homework. Let me turn off the video here.